Good morning, everybody. My name is Alexandra Bell, and I'm the president and CEO of the Bulletin of the Atomic Scientists. Thanks to all of you for joining such an important conversation today. One of the primary reasons the Bulletin was created almost 80 years ago was to connect scientists and the public who could together help shape the policies to manage the nascent nuclear threat. Over time, man-made existential risks have multiplied, so we've broadened our scope to also focus on disruptive technologies, biosecurity, and today's topic, climate change. The risks posed by change are growing by the day, with effects being felt around the world. As storms grow fiercer, droughts intensify, and coastlines change, the existential risks posed by climate change are a significant factor in why the Bulletin's doomsday clock is now the closest to midnight it's ever been. Understanding this, the March issue of the Bulletin's magazine, the Tipping Points issue, is focused on climate change. If you aren't a subscriber to our magazine, you can sign up today. All the information is on our website, and you will receive access to our entire 8-decade archive, along with all future issues. As a nonprofit media organization, we rely on the generous support of donors, sponsors, and subscribers. And we thank all those in attendance today for their continued support that allows us to continue our important work. Now, to briefly introduce our speakers for today, first, I'd like to welcome atmospheric scientist Inez Fung. Inez is a professor emerita of atmospheric science from the University of California, Berkeley, and a member of the Bulletin Science and Security Board. Next, we have climate and sea level expert Robert Kopp. Bob is a professor in the Department of Earth and Planetary Sciences at Rutgers University, where he's also the co-director of the University Office of Climate Action. Next, we have Femke Nice, a complexity scientist and senior lecturer in innovation, energy, and climate at the University of Exeter, and she focuses on the transition to clean energy. So to start, I'll ask each of you to outline the challenges you're seeing in your respective fields of expertise. So Inez, we'll start with you. You're a professor, as noted, of atmospheric science, and your work, among many areas, has focused on the composition of atmosphere and its interaction with the different aspects of biosphere. So could you briefly share your thoughts on what the research is now saying about the health of our atmosphere, especially as new greenhouse emissions information is released on the regular? Thank you.
Thank you, Alex. Great to be here. I want to start by saying that atmospheric CO2 has gone from 280 parts per million in the pre-industrial era, and in April, in March, we have exceeded 420. Okay, so that's a tremendous increase, and at the same time, temperature has increased. So what we're doing, the link between CO2 and climate is based on very firm physics, and I won't go over that, but I want to emphasize where we're going now. What the community is doing is that we are looking, number one, the weather, the severe weather that Alex mentioned, is something that we expect more of. We can attribute now with great confidence that climate change has increased the intensity of storms, of hurricanes, prolonged heat waves elsewhere. So the impact on human health, on infrastructure is great. And the studies show that even if, and this is a big if, magical if, that if we stop the emission, drop emissions to zero, to pre-industrial level, the climate will remain at the same level for a long time. That means that what we have experienced is the baseline. The severe weather that we have experienced is the baseline for what is to come. It will be more severe as we emit more CO2. The weather will be more severe, the droughts, the hurricanes, the tornadoes, and we are entering a climate phase that we have not, human civilization has not experienced. The second thing I want to mention is that now with great computing power, we have much greater confidence in our climate projections. And not only that, now, I think many of you know chaos. that the system, obviously, we have a very nonlinear system in the atmosphere, how it interacts with the land surface, the ocean, and all the chemistry. Um, we now can run a large ensemble. So you perturb in the first experiment done at the National Center for Atmospheric Research, we perturb the temperature. At the time only 40 ensemble members. Now everybody's doing 100 ensemble members. We perturb the temperature by 10 to the minus 12 Kelvin, which is like the truncation error in the computer. Okay, and we have nonlinear behavior. So you can look at the rogues gallery of 40. At the time it was only 40, and you can say, I want to see the El Nino. Yes, it is there. You see the oscillation, the North Atlantic oscillation, all's there. So the challenge of our future is not just how the climate will be changing, but the possibility, the possible states of the climate. And that brings us to the tipping point. So I'll turn it back to you, Alex.
Well, thank you for that, and want to pull those threads that you mentioned as we continue our conversation. But next, I'll move to Rob. You work in I'm sorry, Bob. You work in a wide variety of climate related disciplines. So I'd like to start by getting your thoughts on climatic changes in our oceans. So compared to different time periods in the history of our planet, can you outline current assessments on sea level change and what's happening in our oceans more generally?
You're muted.
Sea level has I think many of you know, is sort of an integrated metric of how much heat we're trapping in the climate, right? As we warm the planet, we're putting heat into the ocean, which causes it to expand. We're warming glaciers, which cause them to melt, and we on longer timescales and through somewhat more complicated physics are causing ice sheets to shrink, right? So all of those are contributing to sea level rise. We know from a combination of observations and geological records that sort of the modern era of global sea level rise started in the late 19th century. Um, it has accelerated over time, particularly over the last 50 years. So the average rate of sea level rise in most of the 20th century was about 6 inches over the course per century. It's now about twice that. Looking at a slightly longer geological context, we can say with an extremely high degree of confidence that the rate of sea level rise since the beginning of the 20th century, since 1900, is faster than any century in at least 3,000 years, and probably substantially beyond that. And we've already turned up the planetary thermostat and put more CO2 into the atmosphere than there's been in terms of the temperatures in over about 120,000 years, and in terms of the carbon dioxide, more than 3 million years. So there's a lot more sort of already baked in. Inez said that to stabilize the temperature, we have to stop emitting carbon dioxide. To stabilize sea level rise, you would have to do more than that, because again, sea level is sort of this integrated metric of how much heat we're putting into the system. So as long as the planet is warmed, it'll sort of gradually equilibrate over thousands of years with that new higher temperature. So basically, the more we turn up the thermostat, the faster sea level rise will rise. But if we were to stop emitting now and stabilize the temperature, we will still see sea level rise for thousands of years into the future. We also know fairly confidently that over the next 30 years or so, through the middle of the century, there's a bunch of sea level rise baked in, regardless of what we do with emissions. So over the first half of this century, we'll probably have experienced between half a foot and a foot of sea level rise. As we get beyond that, sea level projections are more sensitive to how much we emit. Broadly, we would expect about 2 to 3 feet of sea level rise over this century if we don't hit thresholds within the ice sheets that destabilize them. But under a higher emission scenario, we could be looking at 2 to 3 feet of additional sea level rise on top of that. As we'll get to, I don't like the term tipping points for any of this, but there is that instability. There are things we know well, that are quite certainly in store for the rest of the century and beyond. But there's also potential for the ice sheets to contribute substantially more. And we have to make decisions now about how to adapt that sometimes require us to think into those deeply uncertain futures, because we have infrastructure around that will be around in 100 years, where we have a very broad range of futures available to us.
Bob, thanks so much for that. But effectively, are you saying that, 1 to 2 feet is inevitable? And that makes me think of,
Yeah, inevitable. And well, I'd say even 2 to 3 feet by 2100 is pretty close to inevitable. 2 to 3 feet is inevitable. Probably 6 feet is inevitable. But the question is it inevitable in 150 years, or is it inevitable in 2000 years? Right. So how much we emit can place us, can adjust how soon we get to 6 feet. But the last time global average temperatures were as high as they were today, 125,000 years ago, sea level was probably about 20 feet higher than today.
Mm,
So there's reasons why one can't just reason by analogy like that, but it's not unreasonable to think we are looking over thousands of years, if we just stabilize temperature now, at sea level change of that magnitude. If
yeah.
we keep putting in CO2 in the atmosphere, it might not be thousands of years, it might need a couple hundred years.
Certainly something to think about, considering how many people live along coastlines around the world. So we'll put a pin in that and potentially expand a little bit later. But I want to move to Femke. We've talked about the threat. Your focus has been sort of on innovation and mapping of the green energy transition. So that's of great interest to people in the Bulletin community. This is an area, I think, at least from the public perspective, where there's a lot happening, from renewables to batteries. So can you give us an idea of the clean energy storylines that we should be following in 2025, and potentially some good news along with this very distressing news?
Yes, I'll start with the bad news before I go to the good news. So we've heard that we need to bring CO2 emissions to zero. CO2 emissions mostly come from different energy sectors, and what we've seen over the last couple of years is that they continue to rise year on year. There are a couple of big stories here that can change that picture in the near future. The first one is electricity. Renewable electricity has been cheaper than fossil fuels in most countries in the world since 2020. In a lot of countries, renewable electricity plus battery storage is cheaper than fossil alternatives. For electric cars, we're a couple of years behind the electricity story, but there in China, you see that more cars, electric cars, are cheaper than petrols than the other way around. And in countries in East Asia, you see that in the sales as well, where a majority of sales has now become electric. The fact that green electricity, is now cheaper than fossil alternatives means that even in countries where you don't really see strong climate policy, like Pakistan, you see a sudden boom of solar energy, which is putting loads of strain on the grid, but it's a massive story that a country can make that transition even without very targeted policy support. The big questions are those sectors where we don't yet see these stories. We think about residential heating, where the uptake of heat pumps is still quite low. Think of electric trucking, where only China is making headway in that new industry. Think of energy storage, where we still don't quite know what we're going to do with long duration storage. And the big thing to think about when we want to drive the transition in these sectors is, how did we succeed in the other ones where we've got this success, and how can we translate that success to other sectors? There's one feature of these success stories that I think is underappreciated, and that's the low number of countries that started this transition. So for solar, it was a very early 1970s feed-in tariff in Japan combined with Germany's feed-in tariffs a couple of decades later that really started the trajectory towards more mature technologies. For electric vehicles, it was Norway, the Netherlands, and California that not worked together, but had simultaneous policies that combined to really start that transition. And this is something that we can see as well in these other technologies, because when you reach the point where the new technology is cheaper and better than the old technology, you get a self-reinforcing process. I know Bob doesn't like the word tipping point, but you can see that as a tipping point where additional policy might not be needed to get the transition going. Policy will always be needed, however. That is a danger here. Policy will always be needed because the speed of the transition needs to be so high that you can't rely on tipping points alone to make that transition happen.
Thanks for that. In some ways, it seems like necessity might be the mother of invention as we move forward, but that also requires support across the board and investments, including from government. So we'll talk about that a little bit later, about how public policies can affect or detract from these efforts. But I want to go back to something that Inez said about stronger computational power, our increased application of AI tools, quantum computing, improving the nature and the quality of the data and availability of the data on climate change. So how can that increased knowledge help us better understand how to mitigate the negative effects of climate change? And so Inez, I'll start with you.
You're muted, Inez.
Okay, I'm fine now. Thank you. I'll start by saying that whether we hit 2 degrees Celsius, the globally average temperature, yes, there's always uncertainty, but the uncertainty is 20 years or maybe 30 years. Okay, so going back to what Bob was saying, that the infrastructure has a much longer time scale than 20 or 30 years by 2050. Okay, so we're looking at our lifetimes, our not just children's lifetime, but our lifetimes. So where the bigger computing power, the more powerful computers we have, number one, we can have much richer information. We can go to finer resolution, so not to my neighborhood block, yes, for the global kind of, but we can take into mountains, we can take into valleys and urban areas, and so the information that the projections we can provide will be useful for local planning, and that's very important. What crops am I going to plant? And so we're not talking about my backyard scale, but a large farm, a large area like the Central Valley of California or the northern side or the southern part. We have much better information for when the drought, for the possibility, the probability of droughts, of floods, for at that scale that would be useful for planning and for mitigation. That's the first one. And the second one is having the large ensembles, the black swan. You have to, it's a rare event. And so having a large ensemble of calculations, then we can say what is the probability of extreme events. So that would also be helpful for planning.
Thanks for that. I certainly have a personal connection there. I'm from the mountains of Western North Carolina, a place that didn't think it would be
Yes.
affected by a hurricane the way it was with Helene, and sort of creating a once in 500-year flood situation. And, how can data, help us better prepare and plan for that in the future is something, I personally am very interested
But
in.
I want to interject here that Helene is a perfect example of compound risks because it's not just a hurricane, right? There was a storm system, a front that stalled, that rained, and so the soils were soaked. So when Helene came by, the water just can't go into the ground because the ground was saturated. So it's these compound effects that we are learning about, that nature is throwing us more examples and more examples. I've been doing this for a long time, and I feel like I'm playing chess with a smart, not just with a smarter player, okay, who can change the rules, who knows more rules and change the rules on me, okay? So we are looking at a system which is complex, and there could be multiple interactions that we were not aware of in the experience that we have. Okay, so we really are going into a climate space for which we have only scant rules, with scant understanding of what the rules are. So we know a lot, but then there are all these exciting, for a researcher, they're exciting things, but not exciting for the people who had to suffer through the storms, the disasters.
Thanks for that. Bob, so what are your thoughts? How do we play better four-dimensional chess with all these new tools at our disposal?
Yeah, so I look, and many people look at climate change as a risk problem. I already alluded to that, right? There are things that are relatively certain, there are things that are varying shades or deepness of uncertainty, and we have to figure out how to manage all of those, right? So what can we do with more computational power? Well, one thing we can do, as Amy had said, is look at higher resolution. But another thing we can do is more thoroughly look at uncertainty, right? So one form of doing that is is, well, okay, we can run a large global climate model 100 times. We can get, rather than just 30 years of data for the current climate, we can get 3,000 years of data for the current climate. So it allows you to look at less likely events. But he can also do things like explore some of those structural uncertainties. Well, what if the ice sheets are more sensitive? What if clouds are more likely to change, right? You can do a more thorough exploration of physical uncertainty in the system. We can learn, what are things that are hard to characterize the uncertainty of, but that might be important. And also, are there any constraints, things we might expect to see in the coming decades, what sort of things we sometimes call emerging constraints in climate science that would tell us about, be sort of warning signs of being in those things we might think are less likely outcomes. So those are all sort of really important applications of increased computational power. And one of the things AI can help you do is run models more efficiently, right? So you can use artificial intelligence to emulate sort of big complex models so that, right, we don't just have to have 100 runs of a GCM. We can estimate what 10,000 runs of the GCM would tell us. That said, I want to give a caution about like the idea, we invest a lot. We like to invest a lot in better models. But it's not the physical uncertainty that is is the reason why global greenhouse gases are still rising, and it's not the physical uncertainty that's why we're under adapted to the current climate, right? Those are problems that have to do with social systems and governance, and are probably not going to be addressed by stronger computational power or artificial intelligence, right? It requires institutions, it requires people. And so as much as a physical scientist, I want to throw more compute at these problems and better characterize the risk and then better identify what the levers are, I don't think that's actually the first order problem.
Okay. Femke, it seems like AI and new and emerging technologies would have a great effect on the transition to clean energy. But is it coming fast enough? Do we have the right tools in place?
So with climate science, one of the lovely things you have is open science. It's really that philosophy that you can get model output that people can play with it, can build on it. Within energy science, that is not really the case. The big collectors of data are often private companies who ask you to pay a lot for data. So in that sense, as a academic, you don't always have access to all of the data you want to really use AI and these big computes. there is a much bigger question we need to resolve first, and that is access to data among all these sectors, among all these different government institutions and non-governmental institutions. There are some smaller areas where AI will have a larger effect. One of them is, for instance, around optimizing your heat pump, where you can take advantage of, for instance, the weather and optimize when you turn on, when you turn it off. But in terms of the wider picture, I do not believe that it will have a massive effect. Just simply more sophisticated models will make marginal changes, but the bigger changes we need are not around how do we design an optimal system. It is making sure that we have the policies in place to change into these systems. That, for instance, there is a policy in place to ban gas boilers in new buildings where it doesn't make any sense to install them anymore, but people are used to it. So it's still being done. That said, there is probably a negative to this, in the sense that especially generative AI is one of the best ways to generate disinformation. So the effect of these models on climate policy, I expect it to be negative. And we see this again, that there is a rise of disinformation around climate, where disinformation had moved from climate change, the core climate denial, climate's not changing, that was on the wane and is now coming back, which means that maybe there's less focus on the climate denial around solutions, where you also see a lot of misinformation that heat pumps would be noisy, that they use tons of electricity, and so forth. So my assessment of AI, given also that it uses a lot of electricity, is that there might be some good applications, but in general, I fear that it would be a net negative.
Can I just add on that? I mean, I think AI is a marketing term. It suffers from some of the same issues that I will critique tipping points for. Generative AI, I think in many ways, like the really useful power for science of what we used to call statistical regression and then used to call machine learning is being used to sort of put a shine on chatbots. And so when I talk, when we talk about, doing better climate science with AI, we're not in general talking about ChatGPT. We're talking about machine learning methods or emulation methods that are, continuous with what people have been working on for decades. And I think we should be cognizant of, you know, there was a New York Times article a couple of weeks ago about like AI saved this person's life. And no, it wasn't a generative AI chatbot that saved a person's life. It was statistics. And all that, right? And that's what I'm saying, like, there's not, to a large extent with AI, we're seeing more computational power really useful to do statistics. And statistics is not as charismatic a term as artificial intelligence, but we should just be cognizant of that.
Thanks for that, Bob. So, I mean, Femke, you mentioned disinformation. That's an issue that we're dealing with in all this existential risk space across the board, and something we're certainly going to have to figure out better ways to combat and contend with the rise of weaponized disinformation. But at the same time, we're searching for ways to better communicate these threats with people. And so the concept itself of tipping points is a way to describe a moment where something becomes irreversible, positive or negative. But there's some debate about whether or not this is an actual good term to be applied to climate change. So if quickly, because I want to get to some more of the questions that people have, but quickly, just all your takes on the evolution of tipping points as a metaphor applied to climate change, and is it useful in communicating change to the public and policymakers? So we'll start with Bob this time.
Okay, and you're starting with me because we critique this in the issue, which builds on a longer piece in nature climate change. So the term, as far as I can tell, was first used in the late 19th century by engineers, and what they meant was a literal tipping point, right? If you have a water bucket, a water meter for something, right? At some point, it tips over, right? So a literal tipping point, right? Which is a mental model that it conveys, which is sort of a essentially one-dimensional system. You push something far enough, and then it tips over. What we're talking about in the Earth system and in social systems are complex, multidimensional systems. They're in general, I would say, is not a uniquely identifiable point that is plottable upon some axis like global temperature. That is even in theory knowable in advance because if something like the collapse of an overturning circulation. You can run a climate model 10 times with identical forcing, and it will sometimes collapse and sometimes not collapse. Right. So if there's not like a temperature threshold where one would say, yeah, it'll definitely, this is the tipping point. There's an increased risk of the system undergoing a change. So I think it pretty dramatically simplifies what is a quite complex system, and in a way that promotes, I think, misunderstanding. I'd say the positive social tipping points, I like a bunch of the work people like FemCare are doing, but I think there's an older term from Donella Meadows of leverage points, right? With points where small actions can have big effects, which I think actually better characterizes what was trying to do there. And I do think there's evidence that the tipping point framing is promoting misunderstanding. I've seen a lot of things like the phrase 1.5 degrees C tipping point. The World Economic Forum has a website which says 1.5 degrees C is not a policy, not a negotiated policy target. It's a physical threshold leading to large scale tipping points, and that's just wrong. There is nothing we know about 1.5 degrees C other than it is worse than 1.4 degrees C in terms of both gradual climate change and the risk of large scale climate changes, and not as bad as 1.6 degrees C. And if you have people who make that confusion, right, there's a bunch of risks. One is, well, we're going to surpass 1.5 degrees C for some period of time, and it's not going to be that much worse than 1.45 degrees C. And so if people think that the scientific community is saying that there's something physically salient about 1.5 degrees C, that can cause a loss of credibility. Secondly, it can feed into doomism. People say, well, we're going to head over 1.5 degrees C. That's the tipping point. So, well, I might as well give up, not have kids, whatever. And I think that's a dangerous attitude. And third, the other thing that can happen is if you think 1.5 degrees C is something really special, right? Because it's the tipping point, it strengthens the case for doing large-scale geoengineering that, I'm not totally against geoengineering, but I am totally against geoengineering motivated by a misperception of risk. But if you thought 1.5 degrees C was the threshold between, gradual change and catastrophic change, yeah, you should pump the atmosphere with as much of pollution as you want in order to avoid it. It's just not the actual state of the system.
I really appreciate the summation. Actually, you can get the full article. It's in the chat about this issue. Conscious of time, and as I'm going to turn to you, and feel free to briefly touch on the tipping points issue, but more importantly, brought up the idea of how this influences policymakers. And you've been a part of multiple advisory boards, panels, including one that won the joint 2007 Nobel Peace Prize for efforts to build up and disseminate greater knowledge about man-made climate change. So as a scientist who's been able to advise policymakers, what do you think is the role for scientists right now, where it seems like there's been a bit of a rejection of the advice coming from academia and coming from research scientists?
The important thing about science is that for policy is that science is necessary but not sufficient. We have to think about to whom are we communicating the science. Okay, the science, I'm taking climate projection. The fisherman wants the weekly forecast. Okay, the farmer wants seasonal forecasts. Okay, the people who do reservoir planning, infrastructure planning, they want decadal forecast. So we have to think not just, oh, the climate is changing, or this is the one, and sea level rise. Not that. Yes, we use global metrics as our shorthand for among the climate community and for communication. But to communicate it for policy, we have to think about to whom are we talking to? Who would benefit? And not just who would who would suffer if we didn't do it right, if we make an error in the forecast. I'm thinking about fire and floods and what we have been experiencing, but also for the people who plan for evacuation, for the traffic people, we're thinking about communities, we're thinking about people. How do we communicate to the citizenry that this is something that we have to worry about, that we have to plan for? Okay. And so then we also have to talk to the market to say, where the action is. Renewable energy is much cheaper than coal. Thank you. Okay, renewable energy is less damaging to the health of the people who live near power plants and extraction. The extraction places. And so the healthcare costs will go down for you, etc. So there are many benefits that we have to communicate, not just who needs the information, at what scale they need the information, but what the benefits are for doing all the things that we would like, that would help the climate, also will help your bottom line. Okay, so there's a lot of communication. We don't, yeah. So it's the messenger and the message.
Thank you for that. Femke, I wanted briefly, in the same respect, if you have some countries that are going to move forward and take steps to mitigate the effects of climate change, and other states that are not, does that create an imbalance that sort of, undermines the effort? So basically, are regional and subnational efforts worth it, since climate change is not going to respect borders?
Yes, absolutely. And there's two big reasons why it is. One is that the effect of all the other things around climate change, like air pollution, are extremely damaging. So if you just look at the costs and benefits of climate action and you ignore climate change, it still usually makes sense to do quite drastic climate action because it's so costly. 8 million people every year die of air pollution. And that means that most things you do to reduce air pollution, which also reduces climate and greenhouse gas emissions, is worth it economically. The second one is that a lot of climate action is also doesn't need to be global to have a global effect. I talked already about renewables, that a small number of countries managed to really decrease the cost there. China's action in particular recently have made a lot of different technologies accessible for a lot of other countries. So even if other countries don't adapt to these climate policies themselves, they benefit very strongly from these transitions. And it's quite small countries that can do the initial change to market a technology that is needed, like in the Netherlands, where EVs were very economical for a couple of years. That really drove the uptake, and the global industry allowed it to start. So it's good for air pollution and other sort of co-benefits around active travel, freedom for children to travel around if you don't require cars. And it's really good if you look from an innovation and global cooperation perspective, where you don't need to work on it globally, as long as you have sufficient momentum and sufficient number of countries bringing the change forward.
Thanks for that. So there are so many questions in the chat. There's so many more questions I would love to ask you all. So clearly there's more to be done in this space, and hope to potentially pull you into another conversation in the future. But what I'd like to end with, the Bulletin, as many people know, houses the Doomsday Clock, which is a symbol and uh, of how close we are to midnight and essentially the end of the world. But we also like to talk about the doomsday clock of being a way to signal that there are things that we can do to pull that clock back, to turn back the time. So if there's one thing, and as briefly as possible, one thing that each of you think we should do in the climate space to pull the clock back away from midnight, what would it be? And I'll start with someone who helped set the clock. So Inez.
The for me, it's always the cause. It's not just the mitigation and adaptation. The cause of the climate change is greenhouse gases and emissions. So we have to reduce our emissions. And I add that very quickly that over 1 billion people in the world have no access to electricity. And so having access to renewable energy is not just a climate issue, is the health, the education, and everything that comes with the standard of living. So I see that as the not just a climate issue, but having broad adoption of renewable energy is the way to go. It's very important to me.
Thanks for that. And Bob?
I pointed to this earlier, all right? We are not lacking for knowledge pointing to what we need to do in mitigation over the next couple decades, right? There are some technologies that would be nice to have 30 or 40 years down the road that need to be advanced, but we have technologies now. We're not lacking for knowledge about what we could do to adapt. The challenge rests in our institutions. And so unfortunately I can't give you one thing to solve our problem, but I actually think the number one thing we need to address in order to address the climate change is the decline of democratic institutions and the turn towards autocracy. So I think as much as I would like to be the expert on the solutions, this is fundamentally a governance issue, and we can see all around that throughout much of the world, the liberal democratic world, our institutions aren't in good health, and until we address that, I think we're going to be a little stuck.
Right. All right. And Femke?
This is partially related to the previous point. We need to do those kind of policies that are popular and liked and that manage to get these leverage points right. So, for instance, there is a lot of love for walkable neighborhoods, especially the year after you've implemented it. Making sure that we know what kind of policies are loved so that politicians do implement them. And the other one is making sure that we don't do a one-size-fits-all policy. Sometimes we rely very strongly on the carbon tax to do everything. And we know that individuals, for instance, don't really work as a perfect rational economic agent as some of the economic models assume. People have cash constraints. People don't want to go through hassle. So making sure that we create policies like very strong subsidies up front rather than something that they notice 10 years down the line when they make a decision.
No, that's a great suggestion, and I can't tell you how much I've learned in this webinar, and clearly lots more to discuss. Thank you to the audience for great questions. I'm sorry we didn't get to them all, but I encourage you to sign up for the Bulletin newsletter, to subscribe to our magazine, and to keep a lookout for our various events. And again, very clearly, there's lots more to discuss here. So maybe we'll have a part 2 in the future. The next event that we'll have that I wanted to note for you all is an event on May 14th, where we'll be discussing the nuclear threats posed by Iran and how to manage that particular proliferation challenge. that has been around for a while, and of course its direct relation to issues like climate change. As countries around the world look to expand civil nuclear technology, there are proliferation risks at hand. So none of these existential risks really sit alone in the space. They're all interconnected, and that's something the Bulletin is really looking to help outline for communities. So thank you all for being here. Thanks to each of the speakers. Really amazing job, amazing information. So glad you could join us, and thanks everyone in the audience for joining us as well. Thanks.